a very warm welcome to the CDR Swiss Webinar. My name is Samuel Eberenz and I'm a project manager at the Risiko-Dialog Foundation based in Zurich, Switzerland, and also the project lead of the Swiss carbon removal platform, CDR Swiss, who is hosting this webinar on ocean-based carbon dioxide removal with Professor Gregor Rehder and Professor Achim Kopf from the research program CDRmare. I'm very happy to have you here. Before we get into this exciting topic, I will give a brief introduction to the Swiss carbon removal platform for everyone who is watching this and is not part of the platform or aware of our work, to give some context. The Swiss carbon removal platform is a bottom-up initiative by the Risiko-Dialog Foundation in Switzerland, and we founded this in 2021 with the mission to support the scaling up of CDR in a sustainable way and together. Scaling up CDR is where we start our conversation with the target of net zero in Switzerland and beyond, acknowledging that there is no net zero without a certain amount of CO2 that is also removed from the atmosphere to counterbalance hard or impossible to avoid emissions. At the same time, we acknowledge that the big part of this challenge needs to be done by emission reduction, while CDR can fill the gaps of this is what is really hard to emit. Hard to avoid. Sustainability on all levels, not only, but also, most importantly, ecological sustainability and social sustainability, asking questions what biodiversity effects do different CDR methods have, but also what are the social consequences, who bears the costs of carbon dioxide removal, but also the economical and political sustainability, because we believe that any measures that are invested in and built up can only on the long term contribute to our net zero targets if we can pay for it and the political majorities to support this. And together is really at the core of the philosophy for us at Risiko-Dialog Foundation, because we believe it's all about transparency, dialogue, and participation to make such a big challenge happen. With the CDR Swiss platform, we act as a broker of context, opportunities, and knowledge. We foster collaboration and synergies. We have working groups where we initiate new projects, where we exchange across the different sectors. And we also aim at involving the public, the society, and different societal actors with regard to what is going on and what needs to be done. Currently, the Swiss carbon removal platform has more than 50 institutional members from administration, research, research, but also the civil society and business. We have organizations that give money to climate mitigation projects. We have regulators, we have startups and innovators, and we also have scientists from ethics up to engineering. So with this context given, why are we looking at ocean-based CDR now for Switzerland? The reason is that for once, it's nice to have a look beyond our own landlocked country every now and then. And it's not only interesting, it can also become really an important point to develop for Switzerland as a landlocked countries, because there might be, we will hear about this, big potentials for carbon dioxide removal offshore. And in the Swiss climate strategy, we are not only looking at CDR that we can realize completely within Switzerland, but also at the storage of CO2 captured at point sources in Switzerland offshore, but also Paris Agreement Article 6 transactions that could involve CDR completely realized outside the country. And with this, as much context I want to give at the moment, because what we're here for is the input from our experts from the CDRmare research project. So I will hand over to Gregor Rehder now, and I would ask you to also introduce yourself, and we're looking forward to your input.
So welcome also from my side to this seminar. Thanks to Samuel and Christina for the invitation and the opportunity to tell a bit about our project CDRmare here and what it might have in for Switzerland. So what's coming up for today. So I will give a short introduction, a little bit on the background, which Samuel halfway already did. And so it might be taking Olds to Athens, but then go a little bit more into the different options we investigate within CDRmare. And among those, there are two methods which address more carbon storage. And with that, I would hand over to Achim, which might be the most important part from a Swiss perspective. But getting us moved, so already mentioned by Samuel, if we look at the Paris Climate Agreement to keep the climate well below 2 degrees and pursue efforts to 1.5. It is very clear that the main focus to reach this goal is on reducing CO2 emissions. So that's amongst all, and in particular for the first half of the century. But if we look a little bit further into what happened since Paris, then already the GAP report in 2017 by UNEP mentioned that carbon dioxide removal is likely a necessary step. Then there was the IPCC 1.5 special report claiming that all pathways in the in this report, which reached to 1.5 degrees, basically required CDR. And then in the last IPCC report, it's very clear that CDR is a necessary element of mitigation portfolios to achieve net zero CO2 emissions. So this is a very strong one. And it also somehow combines the 1.5 or 2 degrees to not net zero. And if we move a little bit further on in the cross-chapter part of the last IPCC, it's claimed that CDR is unavoidable if net zero CO2 or greenhouse gas emissions are to be achieved. And this was actually taken up by the G7 summit then in mid of last year. So why is that? So what is the link between CO2 emission or residual emissions and the need to reach net zero and the Paris goal? And that's very nicely seen from this graph, which has been updated in the last IPCC report as well. And what it shows basically is a direct link and a linear, almost linear relation between the warming since the mid of the 19th century, so the pre-industrial area, and the cumulative CO2 emissions over that time. And the star you see over there is actually where we have been on the Glasgow meeting in 2019. And what you can see is basically if you move that further into more cumulative CO2, you have a higher expected within the limit of uncertainty, higher temperature. But despite on where this actually ends, which is depending on the path, the slope looks almost the same. And that gives us a chance basically to allow the conversion of a temperature target directly into residual CO2 emissions. So put that a little bit into perspective, if we look at the 1.5 degrees to be reached with a 50% security or likeliness, then you see basically can read from here the amount of CO2 which is still allowed to be emitted in total. And you can also see from that, if you do the same exercise for 2 degrees, that this is less ambitious and gives a little bit more freedom. And in that regard, it's also worth to look at where we are, 1990 on the first IPCC report, or even 2015 Paris, between Paris and Glasgow, that's only 4.5 years. And you can see how much time actually has been, I wouldn't say wasted, but time which has been passed by without somehow going on track to reduce these emissions. So if we look at an envelope of the scenarios which actually reach the 1.5 or 2 degree scenarios, they all have the same components. They have a very strong emission reduction, in particular in the first half of the century. And then you see that it's flattening out. And on the other side here, you see basically on the green line, you see basically negative CO2 emissions. Part of that we're already doing, in particular in the land management. But already in 2030 or so, you see this green part, which is basically other CO2 removal options. And why is that necessary? So in the dotted line here, that's the net CO2 emissions. And you think if it reaches zero, because you have non-avoidable emissions, if you count on that, so you need something to counterbalance that. And if you look at the net greenhouse gas, actually a larger contribution of these unavoidable climate active emissions, which come from the agricultural sector, which comes from non-CO2 emissions, but which would have to be compensated. And the background again is that if we want to stabilize, we have to stabilize we have to basically balance sources and sinks of greenhouse gases to reach a stagnant phase. So that's the background. So we need negative CO2 emissions, CDR, and we need that on top of what's already known like methods like forestry. And this is a picture which actually has been produced for us and our sister project, CDR Terra. And some of that might be very familiar to you if you are familiar with the carbon removal platform, because things like DAX or BECS, forestry management, biochar, they're all noted basically in the portfolio of methods. But if you look at the marine part, here's some other options which are potentially some of them less mature, other are, and some have are very easy to explain if you know a little bit about the land methods, and that's where we are focusing on. But why do we look at the marine realm? That is, if we go, and these figures are from the last global carbon budget, what you can see is basically the deep ocean here is by far the largest carbon reservoir with an exchange on time scale smaller 1,000 years. So in other words, if you would allow these 1,000 years, then 80%, 85% roughly about of the CO2 emissions, independent on where you put it, if you put it in the atmosphere somewhere, would end up in the marine realm, in the deep ocean carbon pool, so to speak, anyhow. And that's on the right side, about 25% of the anthropogenic emissions since the onset of industrialization are now in the ocean. So the ocean already takes its part in climate mitigation for us. But again, we have the 1,000-year timescale. So it's a reasonable question to ask, can we actually force the marine environment to act a little bit quicker as a potential carbon sink? And that's what we do in the mission CDRmare. So we basically investigate how the climate regulating effect of the ocean can be strengthened and in a sustainable and socially reflected way. Who are we actually? We are 22 partners from research institutes, universities, some of them authorities, a couple of members from economy. In total, so we are put together in a mission, which is like a consortium of 6 consortia, so to speak, which are centered here in the middle, with in total more than 200 experts and participants. We started in August 21 for a first phase of 3 years, have just been asked to put in the proposal for the second phase already. And for these first 3 years, we have a total budget of roughly 26 million euro. And actually, so what we basically have, we have 6 projects which interact, and I come a little bit to these 6 projects a little bit sooner. We have a science advisory board from CDR experts all over the world. And we also have like a national expert forum in this group where mostly stakeholders, non-governmental organizations and so forth are in to discuss with us. What's the major aims we have in front of us? So we explore marine methods of atmospheric CO2 removal in terms of potential, side effects, for example, but also in the question of legal aspects and the sustainable use of the ocean, of course. And then from there, we basically have a strong component to inform and advise policymakers with respect to the potential for CDR in the marine realm. And on the long run, we, as it stated originally, we had the goal to develop a marine carbon roadmap for Germany. I think that's badly phrased. What we are actually trying to provide is the role, so to define the role marine options can play in a carbon roadmap for Germany. I think that would be better put. We have 6 projects, and I will talk about 4 of that very briefly and then hand over to Achim. So this is ASMATHIS, which is doing this actually project I'm coordinating, and it looks at at providing an assessment framework and review the individual methods we have a look at. Then we have 3 projects which look at individual groups of methods, which is retake, looking at alkalinity enhancement, C for society, looking at blue growth carbon, blue carbon methods in the coastal region. And we have TestABAT looking at artificial upwelling. And then again, we have these 2 projects, GeoStore and AIMS, Cubed, looking at storage of CO2, so carbon storage in geological formations and in marine formations in this regard. So I will guide you a little bit through that and then hand over to Achim already. So osmosis, that's a synthesis project. Again, we do not really do research on any of the individual methods here, but we basically create a reasonable assessment framework. So to judge or evaluate different methods and in a later step, then basically review the methods which are out there according to this assessment framework which we develop. And at the end, provide an interim synthesis to give an overall picture of the marine options we have. And we have a strong connection to CDR Terra, where I think Samuel is involved as well. And to basically provide the best overlap with the options, or with the evaluation of the options on land. And a special case of this project, actually, we have very strong legal, social, and ethical aspects. So we have more non-natural scientists in the project than the natural scientists. And because we felt that there is kind of the bottleneck in some of the processes and evaluation judgment of CDR options so far. The things we look at are what comes into your mind: effectiveness, technological readiness, permanence, scalability, co-benefits and trade-offs, but also at governance aspects, legal aspects, which are quite different from terrestrial legal situation, because we hit regulations which either are across countries or which in the open ocean has no territorial governance, but international governance. And we have a strong component on the ethical, like in distributive and procedural justice. So has everybody a saying who should be asked? And are burdens and benefits shared equally? So that's just a few of them. And one thing we do is we very strictly introduce a separation between feasibility and desirability of these different methods. And don't want to go into the detail to that. So then we have alkalinity enhancement. So for those who are more familiar on that, it's, if you want so, the counterpart to enhanced weathering. So the idea is the reason the ocean takes up so much CO2 or can do that is because it's buffered by the carbonate system. And on geological timescales on land, enhanced weathering, or in the water, the Earth system reacts to enhanced CO2 or enhanced temperature by enhancing weathering, which enhances the buffer capacity and takes up CO2. And the idea is to basically accelerate this process. So the rates by, for example, providing silicates, which during weathering build carbonate and that binds the CO2, or by dissolution calcium carbonate. Basically, we look at different ways of basically introducing this method, look at different materials, at issues with secondary mineral precipitation. So it's a lot on the kinetics. The potential is tremendously large, but usually the kinetics are slow. And that's, again, why the method is so well observed at the moment. And there is a lot of international project and movement at the moment going on in this regard. Then we look at artificial upwelling, and that, to put a little bit on the land perspective, is a little bit like enhancing growth on land. So it comes a little bit towards forestation. The idea is to pump out nutrient-rich water from the lower water column, which stimulates primary production, so growth at the surface. And if this material sinks, it exports the CO2. That's there is a technical component to that. There are legal aspects as well. So, for example, the upward movement of water is not treated at all from a legal component. And at the moment, it looks at this method deviates a little bit from stimulating primary producers rather than macroalgae, because they have a higher carbon per nutrient load and can be easily and more easily, if you want so, transferred to the deep ocean. So, and then third, and that again is a chain of methods which is being heavily investigated all over the planet at the moment, is blue carbon storage. So restore or even extend the amount of highly carbon fixing surroundings, including mangroves, salt marshes, seagrass meadows, which are all represented down here. And these ecosystems have the tendency to store a lot of carbon, in particular in the underlying soil. So also to put that into perspective, we basically have the alkalinity enhancement, which enhances the inorganic carbon storage. Then the blue carbon options, which go more into the organic carbon, and artificial upwelling, which would somehow be in between. But the ratio for the former two are that if you transfer carbon to the deep part of the oceans, you are getting rid, at least on a timescales of 500 to 1,000 years, and you only get back a small part of that. So that is usually the part of the talk where I would talk about Ames Cubed and Geostore. So the two parts which focus on carbon storage options. But as this is, I think the task which might be more interesting for Switzerland, though in fact through already mentioned by Samuel with the international transferred mitigation options, everything might be interesting for Switzerland in that regard. But again, for that, as we want to go a little bit more in detail over there, I hand over to Achim, if there are no like immediate questions to me, but we want to have a question round at the end. So Samuel, I give the floor first back to you.
Yeah, thank you so much, Gregor. This was very interesting. Yeah, so our idea, I didn't say about the schedule before, is that we'll have these two presentations, but after each presentation, time for some immediate direct understanding, more understanding type questions, and more the discussion questions bundled at the end. So you're very welcome to raise your hands using the reactions of Zoom if you have a direct question to Gregor. Okay, I don't see any raised hands. So if you have questions, you can also put them to the chat, save them for later, and you will still have a chance to ask them. Then I would like to ask Achim to continue with his slides.
Good afternoon, everybody. I hope you can now see my part of the presentation in full screen, so I seamlessly continue where Gregor stopped. And what I want to give you an introduction to are basically two projects which do not look at the carbon capture, but only at the geological storage on one hand in sandstone formations, and on the other hand in oceanic crust. And of course, it sounds a little bit far-fetched from a Swiss perspective, but there's actually a couple of similarities, in particular between Switzerland and Germany, although we are not fully landlocked, which I would like to point out with this slide. This is a recent project that started, and in that you are basically paving two avenues. One is one which is internally solved in Switzerland using captured CO2 to do mineralization and make some more sustainable concrete as a building material. And then the other avenue is more complex, using the CO2 in tanks that go by train to Rotterdam and then on cargo vessels to Iceland. And there you can see the Koda terminal. The CarbFix project, which is ongoing for almost a decade now, is using the CO2 and water, pumps that into the underground, and this way you are mineralizing basaltic crust. And in a sense, now we are coming back to CDRmare, this is a very similar approach we are doing in this project. there's on one hand the consortium GeoStore. This is the national approach, if you want, conventional CCS into Triassic sandstones underneath the North Sea. So this would be the German EEZ. And then on the other hand, the AIMS-Cube project, which I'm coordinating, that's a smaller scale approach in young ocean crust, basically similar to what Carbfix is doing on Iceland, but moving further down on the mid-Atlantic ridge into the deep sea, and we will try and compare the two. Since I assume that there's not only marine geologists in the audience, I would like to point out the key differences between the two. And for this, I have pulled up a figure by Peter Kellyman's paper a couple of years back. Here you can nicely see how you are increasing the storage security depending on the rocks you're using. So for the sedimentary rocks, what you mostly do is to use the existing remaining pore volume in order to trap the CO2. And you can do that to a certain degree, including residual trapping. At some stage, you start to increase the solubility and dissolve the CO2 in the remaining pore water. And then only after a very long time, you start to form carbonate minerals. So for the bulk part of it, you actually need a sedimentary seal in order to make sure that the CO2, which is going in a supercritical state in a couple of meters below the ground, that this is not coming out of the ground and destroys the environment. In AIMS-Cube, we look at basaltic rocks, but we could use any type of mafic rock. And the idea here is to actually push the whole system towards mineral trapping. You can also see that the time scale is somewhat different. So if you do it just the way Carbfix is doing it, use carbonated water enriched in CO2 and pump that into the underground, you have a very high success rate of mineralizing most of that if the concentrations are pretty low. So this way you are turning a greenhouse gas directly into rock if you want for millions of years. But of course, in the basaltic rocks, they are also very porous. You also have the option you have in the sedimentary rocks. So you could use the pore space solely to put supercritical CO2 into the system. So in a sense, you have more choice. And of course, you have old basaltic rocks. You have also very young crust. So your pressure and temperature conditions are also something you can make use of. So I would like to start with the conventional project or projects, if you want. You are probably aware that there's quite a number of CCS projects in Northern Europe going on at the moment. There's Acorn in the UK. There's the Rotterdam Port project in the Netherlands. There's a couple of projects in Norway, the oldest one dating back more than 25 years. That's the Sleipner project. And there's also Snøhvit and most recently Northern Lights. And then you've probably caught it in the press. The Greensand project in Denmark took off, and very recently industry partners joined. So Bifrost is the name of the new initiative. And if you add up the numbers, you are easily in the million tons per year range, where you can actually store away quite a significant volume of the CO2. So how realistic is that, and how safe is that? This is the questions we are usually getting. As I said, Sleipner is going on for quite a while. There haven't been any accidents whatsoever. There's a lot of monitoring going on, and at the moment it's already in the megaton scale of tons of CO2 per year. So if you take that success story into account and project it into the future and look at the entire European shelf, there's quite a substantial volume which could be used. And in a sense, given that you are landlocked, we are partly or almost landlocked, if you want. I think this problem cannot be solved on the own territory, and we have to go into the marine realm to get rid of significant amounts. So how safe is it? Scientists have thought about that as well, engineers also. So there were a couple of CO2 leakage experiments on purpose. Most of them very harmless, actually. The CO2 dissolves in seawater very rapidly. There are potentially lethal effects, but these are very locally restricted. So we are talking about a couple of tens of meters squared on the seafloor, mostly because the water is shallow. There's a lot of dynamics in the water column, strong bottom currents. So in a sense, it's not that much of a hazard as far as GeoStore is concerned. So what are the target regions? Of course, that's the North Sea. All of you know Helgoland. This is where the Buntsandstein, this Triassic sandstone formation, is cropping out at the surface, but there's vast volumes in the underground, and of course there has been oil and gas exploration by many countries, so the underground is fairly well understood by seismic surveys, by drill holes. And one of the first key tasks in GeoStore was, of course, to do a compilation of all these data and come up with a 3D model, a simplified one you can see here. And then they focused in on two areas, one in this western tip and one in the central area, where they did more detailed studies, including numerical modeling. They also basically simulate how to inject the CO2, how far would it go, what pressures are building up or will be building up as a result of the emission on the injection rates in the different formations and areas. So the feasibility study in the broadest sense is going on. And then at the same time, safety first, there's also risk analysis, environmental impact assessment. So GeoStore has also a strong monitoring component, and in particular a geophysical one. They have built passive seismic array with lots of OBSs and some other instruments which will be used in the areas where the site surveys will be coming for the reservoir characterization, and then later on, when it comes to the injection, these will also be used for the monitoring of any noise related to the injection, maybe micro seismic events, hydrofracturing, and so on. And of course, this is the local environment, the benthic organisms on the seafloor, which may be affected in particular if there's leakage, but then there's also the marine mammals. Harbor purposes are very abundant in the North Sea, very easily affected by noise. So this is one of the key elements as well, the physical monitoring. For the Ames cubed, this is a bit of a bulky acronym. I won't read it out to you. It's about the subsea floor storage in the upper oceanic crust. And as I said, this is not industrial scale injection which is planned. This is more a feasibility study if it is actually worth taking something like the carb fix approach into deeper water, where we would have the added advantage that the high pressures there make the CO2 denser. If you mix it with seawater, the CO2 gets heavier, also denser. So in a sense, the likelihood of leakage is really minimized. So what we've been doing so far is geophysical and geochemical characterization of a smaller area off axis at the mid-Atlantic ridge. And then this summer we try and do drill holes there, do a transect in order to find suitable ways to do tracer injection and CO2 injection experiments in the future, hopefully. And then, like in GeoStore, we also have a component where we develop sensors, mostly carbonate system, and also monitoring equipment, including little marine robots, in order to check on the safety of our endeavor. Everything is flanked by analog experiments on the mineralization and also by numerical simulations like in GeoStore in order to bring it to a somewhat larger area. So as I said, deep water in terms of safety, and the key prerequisite is either very young oceanic crust. There, the crust is relatively cold, but still reactive because there's no sediment on top that serves usually as a blanket, like in thermal insulation, like in your bed at home. So that's actually not favorable. So the youngest crust is one of the targets, and you can see on a global scale there are gigantic areas which would theoretically be suitable for CO2 injection and carbonate mineralization. And then these purple areas, these are flood basalts, very porous, sometimes more than 50% porosity rocks where you could store the CO2 as it is without mineralizing it. So these are the targets. We try and quantify the storage capacity, and also do some carbon accounting. How much could we potentially get in? What would that cost? Because you can see some of it is onshore, very easy, or very close to the shore, so here like in Norway and in the European area, but some of it is also very far away. So that's basically a very comprehensive feasibility study. I already explained the pros and cons of the young crust, the low temperature, and also the vicinity of these very active ocean crust areas. This is south of Iceland here, but then also the flood basalt fields, which are basically all around Europe. This is from the opening of the Atlantic Ocean a couple of years back. So as said, we had one large expedition already, identified the fluid flow patterns south of Iceland, found very nice areas where the flow in the crust would actually distribute the CO2, so that with one drilling we could actually mineralize quite a large area. And then the drilling will actually take place with one of our marine robots. This is a seafloor drilling device, remotely operated from the ship. We can drill down to 200, 300 meters below the seafloor, but we could also place observatories in these holes if we leave some of the drill string in. So this would allow us to monitor the crustal processes. But then on top of that, as said, we also have teamed up with a small company, and between academia and this company, we are optimizing the carbonate sensors available, in particular PCO2, then dissolved inorganic carbon, and then pH. We need very robust sensors, rapidly responding ones, because we want to use them on underwater vehicles as well to scan larger areas. And of course, the energy consumption is always an issue. So we are working on that to have a versatile probe for the assessment, not only within our project, within any marine CCS project, and even natural environments, of course. But then we also have off-the-shelf landers. We customize landers and have vehicles on a tether flying out of them on a regular basis. So this is increasing the footprint, which is very important for monitoring of leakage, by 2 or 3 orders of magnitude. And then we have specialized autonomous underwater vehicles, which can autonomously detect CO2 leakage, then go back to that place, take a sample at the in-situ pressures and temperatures. And of course, we use them in all the CDRmare projects and beyond. So in addition to the geology, which I tried to sketch in this very short presentation, we also have a fairly comprehensive monitoring concept, both from the physical or seismic and the chemical side. And at the moment, as Gregor already pointed out, we are asked to prepare the phase 2 proposals. And of course, GeoStore is technically very ready to go for an industrial scale approach if the funding is right, and if industry is joining in, and if all the legal aspects are solved. Whereas Ames Cubed is more in the explorative, still basic research scheme. So we aim for a larger scale pilot project together with some of the other key projects in the area. CarbFix wants to go into the ocean as a huge project in Canada, solid carbon in a cabled ocean network, as projects in the North Sea. I mentioned them in one of the maps, and also onshore, the 4401 project in Oman, which recently got the environmental prize for climate. So we are basically strongly tied to these partners and exchange ideas, and this is also why we are here. We would love to get in touch with all different players and stakeholders in Switzerland, so we are looking forward to the discussion. Thank you.
Thank you very much, Gregor Rehder and Achim Kopf from CDRmare. If you have questions in the audience, you can put them to the chat or raise your hand. Until we get any questions, I've got a few. So this is really exciting. Also, I've got a background from studying in Kiel oceanography. So it's always nice to see these autonomous vehicles, nerdy stuff. My first question, I'll go backward a bit, like chronologically from the presentation, like on Ames Cube. So is this the first research project that really tries to do offshore basaltic storage, or is there anything else on the world?
Well, everything is in its infancy, basically. There's a couple of projects that started recently, but they haven't fully taken off. There's two projects in very deep water. That's ours, and then the solid carbon project in the Cascadia Basin. That's a huge reservoir that would be worth some, well, their estimates go to 750 gigatons of potential storage volume, which would, to put that into perspective again, 3 times the number I put for the sandstones on the European shelf. So that's gigantic. And of course, they are blessed with a lot of technology. There's a cabled network. There have been drill holes by an international scientific drilling program for monitoring. So they basically need an injection site, and depending on how they solve it, a pipeline, and then they could start. Of course, they need a lot of funding, as everybody, and that's usually the bottleneck. But these are the only two in the deep water and the ocean crust I know of. Okay. And then there's a couple of others. The Norwegians are toying with the idea to use some of their flood basalt fields on the Föhring Plateau, for instance. That's easy access. And like in the sandstones and Sleipner, for instance, and so on, they can use some of their hydrocarbon infrastructure and basically just turn things around, do some engineering, and then use it to store the CO2. That's very promising in parallel to the sandstones.
Thanks. Yeah, when I talk to stakeholders on Iceland, that question often appeared, why is the CarbFix approach not taken anywhere else? So this is a lot going on, I see. This first question in the chat. I also got some more questions. So the question from Björn Nissen is, what is the risk of CO2 re-emission or leaks when you're near a seismic zone?
Well, that's a good question after the earthquake in Turkey. I think nobody in his right mind or her right mind would actually do CCS in a seismically very active area, like if we stay in Europe, in the Eastern Mediterranean, for instance. That doesn't make any sense. But I don't know, that's about the natural seismicity, but of course there's always the engineering effort, and from the injection you also have induced seismicity if you don't do it carefully. So that's always something we have to monitor, but we have to bear in mind that, for instance, for all these sandstone reservoirs, these are former hydrocarbon reservoirs, and there is leakage as we speak. But the rates are very, very low. Okay. And nobody can pull up arguments why these rates would go up if you do the carbon sequestration carefully. So we are talking about maybe something like a ton of CO2 per year from one of these seeps areas that affects an area on the seafloor which is less than 50 meters squared. And it is a tiny fraction, if you remember the millions of tons I was listing in the various projects. I don't want to ignore the risk, but I think it is something we can deal with.
Okay, thanks. So I understand that your projects are somehow in the middle of the first phase now. When should we invite you back for like results on feasibility, desirability, and potentials?
That's something you have to ask the funders.
Okay.
If we get a lot of funding, then soon.
Okay.
So to come on that depends on what you want. If you wanted that detailed on our disciplinary work, I would say give it a try towards the end of the project, which would be like 15 months from now. So in the first phase of the project, at least by then we will have for the marine methods is set up of exactly that, an evaluation of what is there. And what might be interesting as you, because we have one component in the project, not only looking at the results of what we're doing within this project, but also what's going on the international carpet. So we will have this kind of overview of the marine options and how that will be followed, which might be interesting for you.
Cool. There's a question in chat. Why are these ocean-based CDR methods not methods to be implemented in the real world? My understanding of this question is, why are the ocean-based CDR methods not included in the carbon markets?
Okay, so I can get there. Yeah, first attempts to do that. There's actually one contaminant in retake to look at the economics of ocean alkalization. It very often comes down to the question, and that's a general question, I think, with CDR options, is towards the accounting and in particular, the monitoring and verification part of that. And there has been a hearing by the EU. You might have been stumbled over that. So it comes down to this is in progress. At the moment, there is no market case for that. You know that is a gray market for that. So you can basically, you can, of course, claim that a method sequesters CO2 and try to find somebody on the green market to basically pay for that, to claim himself carbon neutral. But it's a huge field to basically have that incorporated in the carbon market. There's first steps on that, and it's actually a quite important component of the field. Because on the long run, if you think that big and in a climate perspective, you have to think big, then you cannot do that without a secure investment, which would include that you have to assure that it's somehow reflected in the carbon trading scheme. The other question,
yes,
I think you combine both. I think we can, the beneficial side effects on methods to be implemented in the real world. That is, in particular for the blue carbon, it's really important, I think, because there are a lot of methods which have, due to their restoration, coastal protection component, a very, very strong potential beneficial side from the environmental point of view. So if you think a little bit bigger, there are like two kind of low-hanging fruits. The one is really carbon storage and stay formations, because it's very clear it's long-term gone, and you can potentially very easily account for that. And the other is where measures which would seem very favorable or desirable for you, even if you're not completely sure that you can do the carbon accounting one, and some of the blue carbon options fall into that. And it's a big field actually, because it's also from those who basically have to decide on whether something is allowed to do and so forth. They very carefully look at in particular the environmental effects and potential negative effects, but also co-benefits.
Thanks. The next question focuses on the potential negative side effects in regards to the London Convention on Marine Dumping. How likely are ocean carbon fixing methods like alkalinity enhancements looking to be implemented?
Very good question. So I'm somebody who knows the field. I can even start and potentially Achim also comment on that later on. So the background is that at the moment, everything except research on iron fertilization is not allowed, according to the London dumping protocol. So there is a big debate actually on that. In Germany, you can not even do in coastal waters research on alkalinity enhancement because of a very rigid and enforced interpretation of the London Convention in Germany by the Hohe Einbringungsgesetz, that's how it's called. But there is some movement on that. And one is because in principle, if you look in detail on the definition of dumping in that, there are some potential exemptions which have to do with whether actually your measure is primarily not meant to get rid of something, but to achieve an effect. And this effect has to be without environmental harms. So there is a lot of work on that to make it short. But at the moment, as a hurdle, we have to look at the legal aspects. And as of now, this is an issue. In very strictly speaking, if you look at the London Convention and so the amendment he's talking about, there are a lot of, this is not really put into place because most of the countries haven't ratified that yet. So it's a very, very open field.
Thanks. Because we don't have much time, I still have got a question to Achim. I have got some questions left, maybe with short answers, we can get them in. So for the alkalinity enhancement, I saw presentations on that and that visualized the process, and to me it looked like with the mining onshore, then it needs to be crushed and brought offshore, the material for the alkalinity. It looks a bit like you have all the impacts, maybe side effects of enhanced weathering on land, that you need to mine the material and crush it, but then you also have maybe a terminal to get it offshore and maybe effects on the ocean. So why not just do it on land?
On land, the pressure and the conflicts with the limited area are even larger than in the marine realm. I mean, for the coastal projects, we have the same issues. There's also lots of conflicts of interest, but if you go into the open ocean, that would not be an issue. But of course, economists have to look into that as well, because the transportation, I mean, that's similar to the example to bring all the Swiss CO2 to Iceland. I mean, this is a matter of, well, whether you can afford it or whether you want to invest the money. Of course, I mean, this is bringing us to the question before. Of course, there's positive side effects if you can get rid of something for millions of years and not for much shorter periods like in the blue carbon. But of course, it is an investment, and I think the carbon market is something which will sort of organize itself in the future. I mean, there's projects where the CO2 will be gone forever, like the one in Oman, and they already advertise their premium certificates on the website. But of course, we have to use almost all the available options because the problem is so big. And I mean, what is the other philosophical question? What is a positive side effect? I mean, of course, Gregor said blue carbon, you have coastal protection, but that's why we have many social scientists in the team. If you ask the people living there, they don't want to have algae or mangroves there. They want to have a clean beach and go surfing or something like that. So that's a big of an issue. And then your previous question, why is CarbFix not transplanted all over the place? The answer is very easy. I mean, compared to the million ton and gigaton numbers I presented, CarbFix is in operation since 2014, and I just checked it on the website this morning. They have still only sequestered 88,000 tons of CO2, so it's a very slow process. So you cannot do that in the open ocean. You cannot afford to have a ship sitting there and inject the CO2 for that long.
Thanks. So I still was wondering with the artificial upwelling, how that differs in the effect from the ion fertilization it also mentioned, where in the end for carbon sequestration, we didn't see the effect in the experiments we wanted to see. Is the mechanism different? Do you have hope that it works this time with the ecosystem?
I comment on that. There are several issues with the method as on iron fertilization. There are some difference, and that has to do more with the local governance and steering, which you can control a little bit better. The main issue is one of that you already mentioned with iron fertilization is that even if you stimulate the growth, first it's a relatively large impact on the ecosystem, and then if you fix carbon, doesn't mean that you have to export carbon. So at the moment, and that's I think where artificial upwelling will go in the second phase. There's a relatively there are some advantages on rather than stimulating phytoplankton growth, which iron fertilization did, channeled in a way that you actually create macroalgal growth. The advantage is that you have a way higher C-N ratio in that, and it's basically easier to transfer that to the deep sea as carbon. So that is where it's heading. But again, the method is out there, and it would take half an hour to explain that there are some difference to iron fertilization in that. So there are some differences, but there is also some similarities, which means that you really have to be very careful in understanding carbon pathways and also where mineralization takes place. And again, that's where we're not going. I think the idea of simulating phytoplankton growth will not be sustained for long in that. So the picture will have to change, which you saw.
Cool. Thank you so much. I will show a last slide announcing our next webinar, and showing the slide, I still have a last question for you to think about now. And before we close this webinar, and this question would be, where should we as Switzerland now build our pipeline, send our CO2 in 15 years? And where would you prophecy be that Article 6 solutions for Switzerland could be in the world of the ocean in 20 years? I want to make a small advertisement for our follow-up webinar. So we'll stay a bit in the topic of the ocean-based CDR, but also combine it with insights on US policy on the 16th of March. So save the date. The invitation will go out soon. You can register to our newsletter on our website to get the invitation. And so far as speakers, we've confirmed Francis Wang from ClimateWorks Foundation and Sifang Chen from Carbon 180 with a focus on US policy and maritime CDR pilots in the US. And now we'll close the webinar with maybe a speculative answer from our two speakers on where Swiss CO2 will go in the future.
Okay, maybe I leave it to Achim to tell where to put a pipeline. Just one comment from my side. I think what you would have to carefully look at is the European legislation. And I'm a natural biogeochemist, scientist. So, but in principle, pan-Europe solution, we say, well, some country can basically dispose in another country is easily possible. So it comes back to thinking how Switzerland is actually interacting within the EU on that regard, but can potentially in this regard also be interesting to have a look on that. And for where to dispose CO2 in a geological formation, I hand over to Achim with some famous last words.
Yeah, well, that's really hard to say, but I would probably go for places where the infrastructure from the hydrocarbon or energy companies is best developed, because that will make it affordable. So in a sense, maybe we don't have to build a pipeline at all, but if so, then that's probably some of these areas where we are currently still actively producing hydrocarbons, and of course that has to stop at some stage. That's even more important than the CCS of the hard to abate emissions, and I hope that we will find solutions and have access to these infrastructures rather sooner than later.
Thank you very much for these famous last words. I think the discussion about the role of the fossil industry in CDR and also enhanced oil recovery, etc., we'll leave to the next webinar with our experts from the US NGO field. And with this, thank you very much, Professor Achim Kopf and Professor Gregor Rehder from the CDRmare research mission. And thank you everyone who joined this webinar and stayed with us. So have a nice evening.
Thank you.